All right, take number 3, direction angles and direction cosines. Alrighty, direction angles and cosines. Okay, so we have a vector in 2 space, and the direction vector in 2 space can be described by the angle it makes with the x-axis, alpha, and the angle it makes with the y-axis, beta. Now, in the case of 2 space, this is fairly... Let me go ahead and get rid of this. That's redundant, because if we know alpha, we automatically know beta, because we know that alpha plus beta equals pi over 2, or 90 degrees. But it does not operate that cleanly in 3 space. So if we want to know the angles between the axes and any given vector u, we are going to have to do some maths. Now, what maths do we do? All right. So we're going to use the dot product to find the angles. And we're going to take the dot product of u and our unit vectors I hat, j hat, and k hat. Told you guys those would end up being important. To go ahead and find vector u, the angle that vector u forms with each of those axes. So let's start with angle alpha. Let's go and change it to red. All right, so angle alpha, or the cosine of angle alpha, equals u dot I hat all over the norm of u times the norm of I hat. All right, so we have our vector u. Its components are ux, uy, and uz. And we've got our vector I hat, which is 1, 0, and 0. All right, so when we take the dot product between these two things, 0 times uy is just 0, and 0 times uz is just 0, and ux times 1 is just ux. So our dot product between those two is just ux. Now down here, we know that the norm of I hat is just 1. So our denominator is ux. All right. And so from this we know that our cosine of our angle alpha, my alphas are getting worse by the minute, is equal to the x component of our vector u divided by the norm of our vector u. And I'm not going to go ahead and write it out for the next two because it's the exact same. Cosine of angle beta is uy over the norm of u. The fish hooks. We know that cosine of angle gamma is equal to uz times the norm of vector u. Babushka. All right. So those are called our direction cosines, the cosines of our direction angles. And if we wanted to find our direction angles, we would just take the cosine inverse of both sides, which we will do in the following example problem. Example number 1. Find the angles alpha, beta, and gamma that vector v forms with the x, y, and z axes if vector v equals 1, 4, 7. Our favorite vector, 1, 4, 7. All right. So, you know that the cosine of angle alpha is our x component, which is just 1 over our magnitude, and we've solved this in other videos, but we're just going to go ahead and write it out. Norm equals square root of 56. 1 plus 16 plus 49 2 squares of 14. All right. So, cosine alpha equals 1 over 2 squared roots of 14. Cosine beta equals 4 over 2 squared roots of 14, our y component. And cosine gamma equals 7 over 2 squared roots of 14. We go ahead and plug those into our calculator. We get alpha equals, and we'll go ahead and leave it in degrees. make it easier to conceptualize. Cosine of 1 over 2 forms an angle of 82 degrees with the x-axis. Ooh, that was a clean beta. (57-ish) degrees with the y-axis. And 20 degrees with the z-axis. All right. Now, dividing our x, y, and z components by the norm of the vector, that should bring back some memories. That should ring some bells. What we are doing is we are essentially normalizing our vector. You know, if we have our vector u and we want to find our vector v hat that goes, a unit vector that goes in the same direction as u, we get vx over the norm of v, vy over the norm of v, and vz over the norm of v. Well, we know that that's the exact same as cosine alpha, cosine beta, and cosine gamma, right? Because we got that right there. And so that means if the norm of this vector is u, that means that cosine squared of alpha plus cosine squared of beta plus the cosine squared of gamma is all equal to 1. Cool. That's all we got on direction angles and direction cosines. We will continue our exploration of the dot product.